In 1911, Albert Einstein wrote down an equation for how gravity affects the speed of light. It was brilliant. It was almost right, but it predicted the wrong answer for how much starlight bends around the sun, off by exactly a factor of 2, though nobody would confirm this until 1919. Ultimately, Einstein wanted laws that looked the same in every reference frame, and a scalar field on flat space couldn't deliver that. So, he abandoned it. He spent the next 4 years building general relativity instead, curved spacetime, tensor calculus, and the most celebrated theory in the history of physics was born. But there was a far simpler fix Einstein missed. One exponential. And the story of why Einstein didn't see it, why nobody saw it for over a century, and how it was finally found, turns out to say something important about how physics actually works. Before general relativity existed, Einstein had a much simpler idea. He thought gravity might work by changing the speed of light. This isn't as strange as it sounds. We already know that light slows down significantly when it passes through glass or water. And we already observe light taking longer to pass through gravitational fields. That's called Shapiro delay. We already observe light bending around massive objects. That's gravitational lensing. We just attribute these to curved space-time geometry rather than to light actually slowing down. But what if it really is slowing down at a rate millions of times smaller than glass? You'd have a hard time detecting that in a laboratory, but you'd see it easily at astronomical scales. And we do. Einstein's 1911 idea was exactly this. Mass creates an invisible medium and light slows down as it passes through. What if space near a heavy object has a higher refractive index and light moves a little slower there? In 1911, he wrote his slow light equation. In this equation, c' is the local speed of light. Phi is the gravitational potential, negative near a mass. So c' is smaller near a star. Light slows down. From this, Einstein correctly predicted gravitational redshift. Light climbing out of a gravity well loses energy. But then he calculated light deflection. How much starlight should bend when it passes near the sun? Einstein's prediction was 0.87 arc seconds. The correct answer? 1.75, off by a factor of 2. He got half. 2 eclipse expeditions attempted to measure his slow light prediction. Both failed, one to clouds, one to a world war. Before anyone could prove him wrong, Einstein had already moved on to tensor mathematics and Riemann's geometry. By 1919, Eddington's eclipse expedition measured 1.75 arcseconds, confirming general relativity. Einstein became the most famous scientist in the world. The variable speed of light idea was left behind. A historical footnote. Now here's the part that needs to be understood carefully. Why didn't Einstein just try a different function? The fix is so small. Replace the linear approximation with an exponential and everything works. Let's look at the Taylor series. For small values of psi, like in our solar system, these forms are almost identical. But in the integral for light deflection, the exponential gives you the full psi, not psi over 2. The factor of 2 is fixed. It doesn't just fix the deflection, it fixes everything. Mercury, deflection, redshift. The exponential metric and its equation of motion get them all right. The same answers as general relativity, from a single scalar field on flat spacetime. So why did Einstein miss it? Reason 1. He didn't ask the right question. He never asked, what happens to the instruments inside the field? Clocks and rulers are electromagnetic devices. If the speed of light varies, they must change too. How can one-way speed vary while local round-trip measurements always get c? This forces the exponential solution. The clocks run as e to the minus psi. The rods scale as e to the plus psi. The factors cancel. The exponential is the unique form satisfying positivity, weak field recovery, and multiplicative composition. Reason 2. General covariance. Einstein believed the laws of physics must look the same in all reference frames. To Einstein, a scalar field with absolute time was unsatisfying because it implied a preferred frame. He felt it wasn't fundamental. The irony is that general relativity has the whole argument, a problem of indeterminism that DFD, density field dynamics, avoids entirely. By removing dynamical spacetime, DFD restores unique solutions. Einstein's commitment led him to a theory with a problem DFD solves. Reason 3. The failure felt structural. Einstein thought a single scalar field was too simple to capture all of gravity. He thought he needed a completely different theory, one with far more complexity and a 10-component tensor. But the real solution is a two-sector theory, a simple scalar for gravity and a separate sector for waves. Reason 4. 3D versus 4D. DFD is fundamentally a three-dimensional theory. Space is flat Euclidean space. Time is absolute. General relativity treats 4D spacetime as fundamental. DFD says it's just a useful mathematical repackaging of the optical field. This matters for quantum mechanics. Trying to quantize time itself is the central unsolved problem of quantum gravity. In DFD, the horrific conceptual difficulties of quantum gravity simply don't arise. Time is time. The Schrödinger equation works. Einstein in 1911 had no reason to prefer a 3D formulation, but from a modern perspective, it may be DFD's most important feature. Sometimes simpler is better. A simple scalar field may have been right in front of us all this time. We just needed to look. Thank you for watching. Please like and subscribe if you'd like to learn more about density field dynamics. In our next video, we will dig deeper into Gordon's optical metric.